Okay, let's dive into this. Welcome to This Explainer. Today, we're taking a seriously fascinating journey into the literal building blocks of our universe. I mean, when you look at the world around you, it feels solid, right? It feels real. But if you ask top physicists to define what actually makes up that solid reality, well, the answers get incredibly strange, incredibly fast. Today, we're exploring a brilliant panel discussion from How the Light Gets In over in London, featuring physicist Sabrina Pastursky, and they tackle a seemingly simple concept, the particle. So stick with me, because by the end of this, you're going to be questioning the very chair you're sitting on. Right out of the gate, we have to start with this massively provocative question that was raised during the panel. Think about the device you're watching this on, or, the chair you're sitting in. You were probably taught that everything is made of atoms, and those atoms are made of tiny, indivisible, solid little spheres called particles. We just treat them as undeniable physical facts. But the moderator of this discussion cuts right to the core of modern physics by asking a question that completely challenges our everyday preconceived notions about these indivisible objects. Are they actually real? Or is our fundamental understanding just completely flawed?
Section 1. The particle illusion.
To understand why this is so profound, we really have to recognize this massive gap in how we communicate about particles in everyday life versus high-level physics. The interviewer opens with a radically disruptive premise. They kind of unfairly throw Sabrina right under the bus and ask, what is the difference between a field and a particle? Are particles even useful to us anymore? Should we just do physics without them entirely? I know, it sounds almost ridiculous at first, right? Throwing away the particle? That's literally like asking a baker to throw away flour. But as Sabrina explains, there is a very valid reason why modern physicists are questioning the utility of the particle concept.
Moving on to Section 2, the quantum math problem.
Now, what's really interesting about this slide is that the root of this debate stems from a massive disconnect between tangible reality and quantum field theory textbooks. Just look at the sheer density of this definition. When physics students open a textbook, they aren't shown pictures of tiny billiard balls bouncing around. Actually, as Sabrina points out, a prominent physicist like Steven Weinberg points him to irreducible representations of the Poincare group. And yeah, you might notice the text here says Poincare group, a little phonetic typo, but honestly, it perfectly proves just how confusing and inaccessible this high-level jargon really is. It is completely removed from our conversational understanding of a physical object. So let's break down this heavy jargon for a second. What Sabrina is highlighting is that at the absolute highest academic levels, a particle isn't really viewed as a physical thing at all. It's viewed through the lens of Wigner representation theory. Basically, it's an incredibly abstract mathematical framework, just a set of mathematical symmetries and transformations. It's a concept. Imagine trying to build a bridge, and instead of handing you a brick, someone hands you a complex mathematical equation and says, here you go, here's your building material. That is the utter absurdity of the disconnect happening right now in quantum mechanics.
And this leads directly to Sabrina's main point about why this whole topic is just so incredibly frustrating. People use the exact same word, particle, to describe two entirely different things. On the left side here, we have the abstraction. This is the Wigner representation, theory, the math, the overarching concept used by physicists to describe the universe. But then on the right side, we have the reality, the actual, real physical object, whatever that may be. Sabrina notes that she uses this framework to describe a real object, but because both the abstract math concept and the physical reality are just called particles, it creates a massive, tangled web of conceptual confusion.
Section 3, a question of scale.
So how do we solve this disconnect? Well, Sabrina suggests stepping back to look at the bigger picture. It's not just an either-or situation. The reality of the universe is way too complex for that. She explains that the right description depends entirely on the scale of the interactions you are actively probing. So if you're looking at interactions at a certain scale, it makes total sense to treat these things effectively as point-like objects, what we'd classically call a particle. But if you zoom in and look into the quantum regime, you suddenly start seeing wave-like features. The behavior actually changes depending on how and at what scale you interact with it.
Let's move to and see how this builds into Sabrina's ultimate big-picture takeaway, which is this. Are we playing with frameworks that allow us to describe the essence of nature across all these different scales? We desperately need frameworks that encompass these different facets, where effective descriptions of both point-like objects and wave-like features are totally valid. The fatal mistake in physics, she suggests, is stubbornly trying to stick to just one description and insisting that nature absolutely has to be that way. Flexibility in our scientific framework is completely essential.
Section 4, the classical pushback.
Now, it's worth noting that not everyone on the panel agrees we need these modern abstract frameworks. A counterargument brings up a historical fact. People talked about particles way before anyone knew what the Poincare group was. And this brilliantly illustrates the classical, old-school definition of a particle that most of us learned back in high school science class. The counterargument defines a particle simply and intuitively. It's something that has a well-defined location, and it typically moves along a continuous trajectory through space-time. Think of a baseball being thrown through the air. You know exactly where it is, and you can track the exact continuous path it takes from the pitcher's hand all the way to the catcher's mitt. That is the classical particle. It makes sense, right? It's tangible.
So here we have the Great Divide perfectly visualized. On side A, the classical view, our tangible historical baseball moving in a smooth, continuous line. But on side B, the quantum view, a bizarre, abstract mathematical representation that sometimes acts like a point and sometimes acts like a wave. The classical view feels right to our human senses, but the quantum reality completely shatters it. And, as we'll see, the classical definition actually has one fatal flaw when you subject it to the rules of the quantum universe.
Which brings us to Section 5, Creation and Annihilation. This is exactly where the classical definition completely breaks down under quantum scrutiny. The panelist pushing the classical view asks Sabrina point-blank if she has a problem with the continuous trajectory definition, and her answer? A definitive yes. She absolutely has a problem with it. Why? Because in the reality of quantum physics, we need a framework that allows us to actively create and annihilate particles. Think about it. If something is moving on a permanent, continuous trajectory through space-time, it implies a certain permanence. But the quantum world? It doesn't operate with that kind of permanence at all.
So, the crucial point is this. If you truly believe in the modern quantum reality of particles, you have to accept that they can be created and annihilated right out of interacting fields. They literally just pop into existence and they can pop right back out. They definitively do not last forever. Therefore, a definition relying on a permanent, continuous trajectory through spacetime is fundamentally incompatible with the reality of how these entities actually behave. They aren't eternal little billiard balls, you know? They are temporary, scale-dependent manifestations. We started this explainer by asking if particles are real. And what we've discovered is that the word particle is caught in a massive tug-of-war between abstract mathematical frameworks, scale-dependent quantum behaviors, and outdated classical definitions. We've learned that these fundamental entities don't have permanent trajectories, and they certainly do not last forever. Which leaves us with one final, pretty unsettling thought to ponder as we look at the apparently solid world around us. If the very building blocks of our universe are just temporary, popping in and out of existence, what is actually real?